saw within the last 2 hours for elementary mathematics retakes. But this is the lecture time, and we will be dealing with the special limits that we introduced last time. But of course, we did not have time to finish this topic to see more examples, to solve more exercises, and we will also be able to work a little bit more on general infinitesimals, basically another method that in certain situations is most effective, much better than any other method. So we will be able to you will be able to solve limits in a let's say better way. Yes, question.
Ma'am, you haven't uploaded the master.
Somebody does anyone have a
Yeah, ma'am, you haven't.
I see raised hand.
Yes,
So ask your question, please, if you have a question. If not,
yes,
then
ma'am.
I take it
Hello,
that everything seems to be okay. All right.
hello.
So there we go with the special limits.
Miss, I have a question, right?
We had a few limits of the first kind,
Hello.
and that was the first special limit,
Hello, ma'am.
trigonometric limit, which actually
Hello.
deals with the indeterminate form 0 divided by 0, if that form involves trigonometry, if this form involves trigonometry. So sine x and x, tangent x, arcsine, arctangent, or any combination between these. So we have a special limit. We know that there are these 4 very nice kinds of limits that are all equal
Ma'am,
to
hello.
1, and that enables us basically to find many limits with trigonometry, not completely all, not absolutely everything, but many or most limits that deal with trigonometry.
Hello.
So a very nice classical method. So we were actually manipulating these expressions until we got this desired form. The desired form is this. The desired form is this. So in principle, if we think that I want to achieve sine t divided by t when t tends to 0, I have to adjust these expressions I see in my limit so that actually I see the expression tending to 0
Hello.
inside the sine function, and also on the opposite side of the fraction bar, I should see the same expression. In that case, I will be able to say that the limit of the ratio is 1. Same goes for tangent x and x, arcsine x and x, and tangent x and x. So we say, all right, let's think in terms of t, and t could be an expression of x provided it actually does tend to 0. So if these two expressions are the same, then we are quite happy and we don't have to worry about anything at all. So these should be the same. And because generally it's extremely difficult to change anything inside sine, so we focus our attention, of course, on the expression outside the sine function, because that's much easier to change. And we generally did those adjustments by, let's say, by the help of multiplying and dividing by the same number, or maybe by the same expression. So now I have a couple of examples for you. I made some more examples in addition to those that we considered last time in class. So in this case, we would like to see evidently t over tangent t. Evidently because tangent is below the traction bar and 7x is above. But as we see, so the idea was we cannot change the thing inside tangent, so let's change the outside of tangent. One way, the way I introduced last time, and rightly, there were people who pointed out this is not the most efficient method, but at least it's the most easily understandable. So for tangent 10x, I need to have 10x. So I put the 10x where I want it, and of course, if I multiply by x, I also have to divide multiply by 10x, I also have to divide by 10x. And yes, of course, the x is not strictly necessary. However, if we do put the x there, it actually helps us see very easily, immediately, that we have a limit 1, because that's the ratio t over tangent t, and the remaining things, okay, now we can cancel out x again. So what we have is limit 7x divided by 10x, x and x can be cancelled out, we could divide by those, so we have the limit 7 over 10 or 0.7. As it was pointed out, yes, it's not strictly necessary to multiply by 10x. We could simply multiply and divide by 10. And then this 7x, we would combine x times 10. And then we would not need to cancel anything else out. We wouldn't have these x's to cancel out. That's true. So those who see the whole point can do this without any x's. However, if, as I said last time, this is the first time you actually encounter limits, if you have never really seriously solved limits before at school or previous university or whatever you were doing, then perhaps it's just easier. If I see tangent of t, then I put exactly the expression t up and below, so that I can see very clearly what is going on. And of course, there was something else, and we could cancel things out later. So in a way, it makes sense, because I see I need 10x, okay, I'll put 10x there. And so that was, let's say, that was the classical method. So yes, we could simply multiply and divide by 10 without that extra x, because the extra x, as you see, gets cancelled out anyway. That's perfectly fine. Next, the same kind of limit can be used when we are dealing with expressions like 1 minus cosine something. In this case, I would say the easiest thing to do, mostly, arguably, of course, the easiest thing to do is multiply by the conjugate sum, because that's something that's easy to remember. It's a bit more difficult to remember how to change 1 minus cosine something into sine squared, for example. We have the formula. We could do it according to the formula, but I am using this method simply because it is, let's say, maybe a little bit longer, but it's simpler. It's simpler to multiply by a conjugate expression. It's fairly simple to open the parentheses, apply the formula, and have 1 minus cosine square of 4x, a minus b times a plus b, and the other part remains as it is. This was cosine, sorry. 1 plus cosine 4x, and then we see we can go on limit x tends to 0, sine square 8x. We see that this particular limit tends to 2, because cosine, remember, cosine of 0 is 1. So basically, when x tends to 0, in those parentheses up above the line, we have 2, something that tends to 2. And so I could just take, okay, 2 outside, so that we are not bothered with this part anymore. Just take 2 outside. And below the line, 1 minus cosine square actually is sine square of 4x. Now, it would be very easy to say, okay, so it's 8 over 4, it will be 2. No, this limit is not equal to 2. That's because we have squares. That's and times 2, right? That's because we have squares. So remember, again, let's say a simple thing to do, maybe not the shortest, but simple enough thing to do would be, for example, expanding sine of 8x, sine square written as sine 8x times sine 8x, sine 4x times sine 4x. Or we could see that if they're both clean, pure squares, square divided by square, I can simply have, sine of 8x divided by sine of 4x squared. And from there, we have a variety of approaches, different kinds of approaches that we might have. One possible approach is, if you are clever enough to notice that 8x is 2 times 4x, and if you remember the formula, sine of double angle 2 alpha is 2 times sine alpha cosine alpha, then you might, expand sine of 8x into 2 times sine 4x times cosine 4x, simplify sine 4x, and there you go. So that would be a very good approach, simply because it is using trigonometry, and it's using trigonometry effectively. So if you know this formula well, and if you notice that indeed 8x is twice 4x, then you can do it this way. So we could have it like this: 2 sine 4x cosine 4x divided by simply sine 4x, and then, of course, squared. And then you say, okay, sine 4x, let's delete those. And then we know that cosine of 0, as x tends to 0, cosine of 4x tends to 1. So we have 2 times 1, and that's squared. So basically we have 2 times 4, which is 8, this limit. That would be limit using not so much limit methods, rather than clear trigonometry. However, it's not always that we can use this method of double sine of double angle. So in that case, we would, if we had other numbers, not 8 and 4, but let's say something like 7 and 3, or 5 and 18. In that case, we would not be able to use any formula like that. In that case, we would do, let's see, another approach, the classical approach. The classical approach would be to limit, when x tends to 0, sine 8x divide by 8x multiplied by 8x. Now sine 4x below the line, and then all of that squared. So in principle, sometimes we might need this other number as well, 4 and 4. But in this case, we see here, we have sine 8x divided by 8x. Sine 8x divided by 8x, that's 1. And here 8x, we can think of it as 2 times 4x. So instead of this, we will think 2 times 4x. And then we would have another 1. So we can have 2 times 2 square. Because here we see, of course, this 2 is remaining. So again, we would have the same thing, 2 times 2 square, which is 8. And of course, if we had other numbers, we might have another number squared. So there are different approaches, and basically a good mathematician or a good student of mathematics will generally see and recognize the most efficient way, the best way of dealing with this. And of course, a very quick reminder, we also have a formula for the double angle. 1 minus cosine alpha actually equals 2 sine square of half angle. This is the formula for the half angle, how to get half angle from the whole angle. So if I have 1 minus cosine alpha, 1 minus cosine something, I could simply change this directly into 2 sine square of half alpha is 2x. And then I would be able to deal with the situation, let's say, in a slightly different manner. However, we would still use the same ideas we would still use the same ideas as we did in this previous method. So it's up to you. You may use this method from this formula from trigonometry. You may use any other formula from trigonometry that you remember and that seems useful. Or we can use simple algebraic methods where the only real thing from trigonometry to remember is that 1 minus cosine square can be rewritten as sine square of the same angle, and that cosine of 0 equals 1. If you remember more formulas, then of course they are welcome to use those. However, I would ask you to comment, to explain what you are doing there, what you are actually using there. All right, so some more limits from the trigonometry, some more trigonometric limits that we have left over from last time, from Wednesday. And so in this case, it would seem, what does it seem? What does it look like? It looks like infinity minus infinity. This one is actually infinity minus infinity, because 1 divided by 0 is infinity. 1 divided by 0 again, infinity. We don't like, basically this is the least pleasant of all indeterminate forms, because it cannot be resolved directly and immediately. However, it can be resolved if we change this indeterminate form into something more familiar, like 0 over 0, infinity over infinity, and things like that. So let's change this. Now, this limit does require a little bit of trigonometry. 1 divided by sine x, 1 divided by tangent is actually tangent reciprocal. That would be cosine divided by sine, because sine divided by cosine is tangent. Here we have the reciprocal, turning things upside down. So what we have here, limit when x tends to 0, write everything on the same line. Sine x is the common denominator, and the numerator 1 minus cosine x. Now this is going to be maybe interesting, maybe not. This limit actually is going to be equal to 0. In this case, it seems that these two infinities are actually identical in some sense. So in this case, I will actually use trigonometry, or I might simply multiply by the conjugate sum. Well, actually, yes, the multiplication by conjugate sum is easier in this case. So I will do the following. I will erase this part, and I will extend. I will extend the fraction bar, and I will say, okay, let's multiply by the conjugate. Beautifully, if we do that, this will be very obvious. If I don't multiply by the conjugate, remember that the formula involves half angle. So who wants x half if I can stay with just x? That's not the most pleasant thing. 1 plus cosine x. So we have limit x tends to 0, 1 minus cosine square x divided by sine x, 1 plus cosine x. Just remember that 1 plus cosine x tends to 2, because cosine actually approaches 1, so the whole parenthesis tends to 2. I can take 2, but below the line, of course, from the denominator, I can take it in front of the limit. And then we have sine square x, because 1 minus cosine square is that. This 1 plus cosine is already out, this 2 here, and we have sine x. So we see we have 1/2 limit when x tends to 0 of simply sine of x, because one of the factors sine x cancels out. If x tends to 0, sine x also tends to 0. So we have the zero limit. This is the zero limit in the end. So you see that trigonometric limits require knowing how to manipulate limits on one hand, but on the other hand, what is also really necessary is some understanding of trigonometry. By the way, I'm reminding you, next week, next Wednesday, we are starting the revision, the work with trigonometry in elementary mathematics. That's the last huge chapter in elementary mathematics starting next week. Now, this looks, I would say, a little bit strange, because this doesn't look like our normal, regular, ordinary trigonometric limit. It looks different. So what we could do with this is, let's say, and x does not tend to 0. So, but let's see, if x tends to 0, if x tends to 1, then this, in fact, does tend to 0. So what if we use some substitution? So what if we say, all right, let's denote 1 minus x, let's denote it by some other variable t. So then, if x tends to 1, then evidently t tends to 0. And of course, we should need to express x. X could be written as 1 minus t from there. And now let's rewrite this limit. Maybe it will look better now. Limit when t tends to 0, t times, right, 1 minus x is t, times tangent of pi times, instead of x, we have 1 minus t, all of that divided by 2. Now we have to see what is next. What is next? We see this is still limit, t tends to 0, t times tangent of something. Now I am going to change this a little bit. I will have, opening the parentheses, pi divided by 2 minus pi times t divided by 2. I'm simply splitting this. And now again, we have some trigonometry. Remaining, trigonometry to deal with. Remembering something that for example, in a right triangle, remember that the sum of the acute angles is a right angle. And what is the sine for one of the acute angles is actually cosine for the other one. And what is tangent for one of the right angles is actually cotangent for the other one. So basically, we could understand that tangent of 90 degrees, that is pi half, minus acute angle alpha, is actually equal to cotangent of alpha. Because if one acute angle is alpha, then tangent is opposite divided by adjacent leg. However, this other angle is right angle minus the first, 90 degrees minus alpha. And for that angle, what was opposite leg to the alpha is adjacent to 90 minus alpha. What was adjacent to alpha is now opposite to 90 minus alpha. In other words, tangent of one acute angle in a right triangle is the same as cotangent of the other one. Or in general, we can see that I can rewrite tangent of 90 degrees minus some angle alpha as cotangent of just alpha. That's angle reduction. So I see that I can, in this case, use this situation to my benefit. This is 90 degrees and this is alpha. Tangent, 90 degrees minus alpha, is actually cotangent. T times cotangent of this alpha, the remaining part. Pi times t divided by 2. Then, of course, we remember that cotangent is tangent upside down. So I can still rewrite this same limit as t divided by tangent of the same pi t divided by 2. And basically here we see we already almost have the limit, almost. So cotangent, of course, is 1 divided by tangent, which we use. And now we have almost tangent of x divided by x. So to get pi times t divided by 2, I must multiply by pi divided by 2, multiply by pi divided by 2 to make these equal. But then to cancel this out, I also need to multiply by the reciprocal. I multiply by pi over 2, and then I multiply by 2 over pi. So both the yellow parts cancel out because the product of the two yellow factors is 1. But I need one of these yellow factors simply because I want this. And so I see that this limit is actually equal to 1. And so my solution turns out to be 2 over pi. This is a rather complicated limit. This is rather, as you see, you need to be able to use trigonometry. Trigonometry is, yes, we all know, trigonometry is perhaps for many students, it's the least favorite part of school mathematics. It happens. All right. So for this, we needed to introduce some kind of substitution, some kind of transformation. Without that, it would be basically impossible to solve this limit. Here, this one is quite nice again. Not so very bad. So yes, again, see, x does not tend to 0. However, sine of something that does tend to 0, x minus 1 does tend to 0. X tends to 1, then x minus 1 tends to 0. And x squared minus 1 also tends to 0. So yes, we do have a trigonometric limit. So what we will do is, at the moment, I am not going to use a substitute in the first part. So x tends to 1, and I can still write sine square of x minus 1. And then in the numerator, I can write x minus 1 times x plus 1. Now, in this case, it's pretty, I would say, useful. Evidently, it would be quite useful to expand the sine square into simply. No, I don't hear you.
Excuse me,
for some reason. I don't know why.
Excuse me.
Okay, wait. If anybody is saying, okay, now, okay, try now.
Excuse me, miss. Can you show previous slide for me?
Previous slide. All right. Yes. Now I can hear you. All right.
Miss, I have one question, right?
Okay, thank you, miss.
When will we mark our retake? When will we get our retake test?
Why everybody shouting at the same time? And music and whatnot.
Excuse me, miss. Thank you.
Okay. So I'm moving back to the next slide. All right.
Yes, so the question is, I want to know, when will you give us our retake 3 marks? Or is it?
When I have done them, I have had 3 or 4 examinations in the last week, and I have to read everything. As soon as they are done, you will get them.
Okay, miss, sure.
Relax.
Thank you.
And it would be very nice if you would not interrupt mathematics with other things. You could keep these questions to the end of the lecture.
Sorry, miss, sure.
So now, we could expand the sine square. We could expand sine square into sine times, again, the same sine. It's a square, after all, of the sine, divided by x minus 1, x plus 1. Now we see x minus 1 tends to 0 because x tends to 1. So this limit is sine t over t when t tends to 0. So this limit is 1. However, here we see when x tends to 1, we have sine of 0. When x tends to 1 in the denominator, we have 1 plus 1, that's 2. So this limit is 0. This was comparatively easy. It's just that one way of looking at this, okay, you look at the standard situation, but what you need to see is also sometimes you need to see one step further. So something that at first does not look familiar at all, and you have to think a little bit to notice the pattern to see what makes things more familiar. Moving on. When x tends to pi half, okay. When x tends to pi half, we could see that pi half minus x tends to 0. So perhaps again, maybe we need to rename this t, where maybe we need a substitution. So suppose t is pi half minus x. In that case, of course, x is pi half minus t. And when x tends to pi half, evidently t tends to 0. So basically, if we move to this new variable, if we stop using x, but start using t, then we might have something more useful. We would have limit. Instead of x tends to pi half, now I can write t tends to 0, because that's what it does. I can write 1 minus sine. Instead of x, I can now write pi half minus t. And instead of pi half minus x, I can write simply t, but it's of course squared. Now we notice again the same thing. If we have the angle alpha and the angle 90 degrees minus alpha, we have to remember that for these angles, what is sine for one of these angles equals cosine of that other angle. We did discuss this a few minutes ago for tangent, but in principle, we already used it before when we were discussing the angle between a line and a plane. What was cosine for one angle was sine for the supplementary angle. So this sine of pi half minus t is actually cosine of t. This is actually cosine of t. I can say that cosine of angle alpha is the same as sine of the complementary angle in the triangle. And so we have 1 minus cosine t divided by t squared. Now, we already know what this means. In this case, I will use the formula because it's simple to use. It's the angle t is just simple. It doesn't have any constants anymore. So I write this is 2 sine square of t half. From the formula we had on the board a few slides ago, that was this one in the corner. This formula is useful now. How to move from the 1 minus cosine some angle to sine 2 sine square of half angle. And that's what we actually are doing here at this moment. 1 minus cosine t is 2 sine square of half t. And we have t squared. So now, of course, I need t half and t half for the sine square. We can resolve this in a variety of manners. So I would say, again, without thinking too much, I will expand it because this does not require much thinking. Sine of t half times sine of t half, and here we have t times t. So now what do? We divide by 2 and we multiply by 2. We divide t by 2 and we multiply by 2. And so we see, again, here we can see beautifully We can see beautifully these limits. There we are, those are 1, and so 2 divided by 2 times 2, this limit is 1/2, and that's it. So this limit is easily found. Again, of course, we could multiply by 1 plus cosine t. We could use the previous method, which is what many people actually prefer. So I could multiply by 1 plus cosine t by 1 plus cosine t. That's a different method altogether. So we would have limit of sine square t divided by t square, and this ends up being 2 when t tends to 0. And this is very clearly, you see, sine square of t divided by t square. This is very clearly the standard limit just squared, 1 squared. And yes, times 1/2. So in principle, it was possible to do it this way. I simply wanted to remind you, this about this other method. So now we have 2 basic methods for this situation where we have 1 minus cosine alpha. If everything goes well today, towards the end of lecture, we might have another way of dealing with it. Another way of dealing with it, which is basically, it can be proved by, let's say, it can be proved using this. It can be proved using these methods, but let's say a nice shortcut, so to say. There is one. And now, the second special limit, so it was the situation where we had 1 to power infinity, which is not 1 because in this indeterminate form, if this is indeterminate form, 1 to power infinity, we are not thinking in terms of 1 as a number. 1 is not a number, 1 is something that tends to 1. So not quite. As we see in this limit, not quite. A little bit more or a little bit less depending on the sign. And if this x tends to infinity, then this really becomes very, very little added or subtracted. 1 over x approaches 0. However, something slightly more than 1 taken to an infinitely large, to a very large power, is not 1. It's still greater. And basically, it can be demonstrated that this is this magical number, if you like. So we were using it last time for one limit that was rather complicated. And I just rushed it at you because I wanted an example, and that was an example on my presentation. We will start with simple examples. So let's have a look at this. So what we want something that looks like this. 1 plus 1 over t, everything to the power t, when, of course, t tends to infinity. Here we have something completely different. So what we do in these cases, again, we simply substitute. So let's say I want 1 plus 1 over t. I have 1 plus, yes, something. It does tend to 0. Yes, of course, I see that this does tend to 0, but it's not 1 over t. So I will simply rename it. I will say, suppose 3 over 5x is now called 1 over t. That's it. It is now called, let's now call it from now on, 1 over t. And I understand if x tends to infinity, then t also tends to infinity. Clearly. And now I can rewrite this limit. 1 plus 1 over t to the power, yes, I would need 10x plus 3. When x tends to infinity, and I can write t also tends to infinity, if you like. So I don't really want this. I want t. So what I do is I multiply by t, And I also divide by t, multiply by 1 over t. So this t times 1 over t, this is a very, let's say, I would say this is a clever method. And this is basically, it is, let's say, the fastest method. This is the fastest method. So this is actually, this product, now yellow, is actually equal to 1. However, we will use it in a split way. I actually did introduce this product with the purpose of using t separately. That is, I am taking this, because now I see this limit is actually e. And yes, I have something else outside. I have e to power whatever. So I will still need to sort that exponent out. I still need to consider this exponent. So what I see now is the limit of e, the red part is e to the power 1 over t times 10x plus 3. But let's remember 1 over t is something that we have actually set up as, well, artificially, more or less. It is actually 3 over 5x. So instead of 1 over t, I do write 3 over 5x, that's 1 over t, and then I need to multiply by this actual old exponent because it never disappeared. It's still there. It cannot just disappear. So I'm writing 10x plus 3 multiplied by this 1 over t. And now I understand, of course, x tends to infinity. T is lost again. We took t, we introduced t, we used it, and then we said, okay, thank you, we don't need you anymore. And now, of course, we have to figure out what this limit is, what this fraction says. We can, if you like, do it separately. So we can do separately this thing, limit when x tends to infinity of 3 times 10x plus 3 divided by 5x. So that is limit of 30x plus 9 divided by 5x. When it's infinity, now dividing out x, remember we did divide out x. X tends to infinity. We have just 30. We have 9 over x. Please don't forget to divide 9 also by x. Divided by 5x divided by x is 5. And so we say that this is 30 plus 0 divided by 5. This is 6. So in the end, from this, I can conclude that my final limit is e to the power 6. E to the power 6. So in a way, we again transform, like with the trigonometric limit. What we did with trigonometric limits before, we kind of force the expression into the form that we like. We had some expression. We had squares, we had x's, we had 1 minus cosine, and we transformed. We introduced, if necessary, substitutions, but we were forcing that limit into the form, into the pattern that is familiar to us. Same goes on here. So I have 1 plus something that tends to 0. All right. I will denote that something which tends to 0, I will denote it 1 over t. And that's it. And then I'll see what happens to the rest. Of course, everything must fit together correctly. But the thing is that we are thinking about what form do we want? Aha, we want 1 over x. All right, let's make it 1 over x, or in this case, 1 over t. There is another method of dealing with this as well, one from which we express x. From this, we still use 1 over t, but then we express x, inserted in there into the x in the exponent, and then we do some clever thinking, some clever tricks. However, that requires, again, an extra explanation. Sometimes people dig out that method from somewhere, which is, I don't think, a simpler method at all, but they miss the explanation part. Okay, so something similar, only the expression is now more complicated. In the second example, we still say, okay, so t, 1 over t, 1 over t, I need a razor. Okay, we have 1 over t will be minus 6 over 2x plus 3. Please note, the formula has a plus. The formula has a plus, and therefore, because I need plus 1 over t, I take the minus into t. I take this together and say this will be plus 1 over t. So that's why I do have that minus sign in there. And of course, if x tends to infinity, then t will tend to, okay, in this case, it tends to minus infinity. The thing about this limit is that it works. It doesn't matter whether t or x tends to positive infinity or negative infinity. As long as it tends to infinity, it's everything is all right. Now, okay, let's see how things work out for this. So we have limit when x tends to infinity, and t also tends to infinity, but only it will be minus infinity, but in this case we can just write infinity. 1 plus 1 over t as we substitute. Then we want t times 1 over t. That is universal. We want t, but to cancel it out, to balance things, we need to again multiply by 1 over t and multiply by the actual. Now we put the real exponent, which is 5 minus 3x. Now in this case, we will have, again, I will mark what is e in this case. Let's make it green this time. This is e, actually. So now we can write. We can write limit when x tends to infinity. We can have e to power. Now 1 over t is actually this. So I write, instead of 1 over t, I write minus 6 over 2x plus 3 and multiplied by what we have, 5 minus 3x. So 1 over t is this part, and then 5 minus 3x, of course, it needs to be included very carefully. And again, we know that it will be e to some power. Now, again, I can take separately limit when x tends to infinity of this exponent. And that is minus 30 plus 18x divided by 2x plus 3. If we divide out the highest power, which is x. Then we have minus 30 divided by x plus 18 divided by 2 plus 3 over x. Once again, I remind you, don't forget to divide constants by highest power of x. In this case, it's just x. So we see that we have 0 plus 18, 2 plus 0. So it's 18 divided by 2, that's 9. And so that is the exponent. So the final result is e to the 9th power in this case. So there is another method which I don't particularly want to introduce now because that would require, as I say, extra explanations, which is why it's not so good if you use other methods in a test, in a unit test or in an examination without any notes, comments, explanations. Because I have explained one thing and I'm perfectly willing to accept that for granted. However, if you use another method, something different, then you should actually explain this method, what you are doing there really, or why. Now, another thing, when x tends to 0, it's still something. It's not exactly 0, so it's still 1, but slightly off 1. Because x might become very, very small, but still is something. And then we have 1 plus added something. It's still greater than 1. And here we see 2 divided by 0. That's infinity. So we still have 1 to power infinity, this indeterminate form. But the first rule is, of course, always check x tends to what? To 0, to infinity. What happens with things? How to solve this? Well, there's nothing new. We do exactly the same thing. We would say this. So let's say 1 over t is what we want. Okay, let's denote 6x by 1 over t. And then if x tends to 0, this means t must tend to infinity. And so we would have limit x tends to 0, but at the same time t tends to infinity. Nothing wrong with writing down two variables. Where does x tend? Where does y tend? T tend? And now we have 1 plus 1 over t. We substitute 1 over t for 6x. Then we need t as always. Nothing has changed. Then we need 1 divided by t to cancel out t, nothing is new, times, of course, the actual exponent, which is 2 divided by 3x. And once again, I will use a color to show that this limit is e. And so we have limit of e to the power 1 over t. Now I say, okay, it's 6x instead of 1 over t. So I can write it 6x times 2 divided by 3x. And this is so easy to find. X cancels out. So we have e to the power 12 over 3. That is e to the 4th power. This is even easier than the previous one. This is easier. We did not have to go somewhere on the side to find the limit of the fraction. It was already visible. Okay. Now this is from one of your exercises. This is already somewhat similar to what we did last time. So we had a fraction in parentheses, and then that fraction is taken to a power that includes x. That means also tends to infinity. So first of all, we need to check that this limit is indeed the indeterminate form 1 to power infinity. That's something that we need to verify and make sure that we understand what is going on there. And so we can have, well, some transformations. We can do them somewhere on the side so that we don't mess up the computation of the limit, this part. So I can actually do it somewhere there. I would say, all right, so 3x divided by 3x minus 2, I want to change it into something, 1 plus something. So to get perfect 1, 3x minus 2, I would need 3x minus 2. This is 1. But of course, I do not have really 1. I do not really have 3x minus 2. I have just 3x. So if I subtracted this 2 artificially, it wasn't there, so I invented it. Why did I invent it? Because it fits the denominator. We have 3x minus 2 in the denominator. Why cannot we have 3x minus 2 in the numerator? But of course, what we also actually have is just 3x. So I am adding 2 back. So in principle, I am transforming this expression, starting with, I need to duplicate the denominator. I need to repeat the denominator. Then I have 1, but of course then we need to correct the error. So we have 1, this part is 1, and then we have plus 2 that could not be divided, the remainder divided by 3x minus 2. So this is so far so good. Now the next thing is, now we will substitute 2 divided by 3x minus 2 by 1 over t. And we understand that if x tends to infinity, then t also tends to infinity. So now at this point, at this moment, I can return back to my original limit and start working on that lim x tends to infinity. Here we have, 1 plus 1 over t from this to the power, the same as always. It's very much standard. So if we do this many times, you should probably remember what happens there. So we put t, we put 1 over t, and we put the actual 6x minus 1, the real exponent that we actually had. And now what happens is the same, more of the same thing as always. We say evidently this is e. And so we have limit of e when x tends to infinity. 1 over t is in fact this. This is 1 over t, so I write power 2 divided by 3x minus 1, that is 1 divided by t, times this real exponent that we had, 6x minus 1. And when we open this, well, basically we would have e to power 12x minus 2 divided by 3x minus also 2. X tends to infinity, and now everything depends on whether you want to do this limit on the side again, or you can manage it in there. We understand that if we divide out x, we can do it here on the spot. We don't have to do it on the side. We have e to the power 12 minus 2 over x, and here we have 3 minus 2 over x. So this is again e to the power 4 minus 0, 3 minus 0. So it's e to the power 4 thirds. Sorry, not 4 thirds. Wait, 12. We have e to the power 4, sorry. I got carried away. Was looking at something that was not there. (12 minus 0, 3 minus 0, so we actually have e to the power 4 as the final answer. So the thing is that, yes, it's very difficult. We would need a calculator or computer to find how much is e to the 4th power. That's something, but on the other hand, why bother if we don't need it for practical purposes? Then there's no need to figure it out more exactly. E to the 4th power is a fine answer. It's obvious that this is a constant. If this is a constant, then it can be found using a calculator, which we don't need at the moment at all. All right. What else do we have? Some similar limits where we might use the e limit, but which are not at the moment. At the moment, they are not e limits. They have logarithms. So what we can do with this is, logarithm divided by something. It's not very promising at first. At the beginning, it doesn't look very nice. So what we can do, I can think, 1 divided by x times logarithm. It's not much different, I'm simply, instead of logarithm divided by something, I now have logarithm times something. But now remembering logarithm properties, what we have to do is we take the factor in front of logarithm and move it, and we make it the exponent inside the logarithm. So we have limit when x tends to 0, ln of 1 plus 5x, and this 1 over x goes inside, becomes exponent at 1 plus 5x. All right, so now we should figure out what happens to this 1 plus 5x to power 1 over x. So it's 1 plus 5x to the power 1 over x without logarithm. When x tends to 0, all right, I am writing limit of this when x tends to 0. And we had something very similar, slightly more complicated. This is very simple. Remember that what we did was, let us suppose that 1 divided by t is 5x. So t tends to infinity, of course. And so we can write limit 1 plus 1 divided by t, again, as always, times t times 1 over t times actually 1 over x. And so we have, so when x tends to 0, then t tends to infinity, of course. This means that, again, we have e to the power 1 over t. 1 over t is 5x. 1 over x times 1 over x when x tends to 0. So in fact, we see x and 1 divided by x cancel out. So we have e to the power 5. And now this is like limit when x tends to 0 of ln, because ln was not touched here. But this, the limit of this inner expression, is e to the 5th power. And of course, ln of e to the 5th power is just 5. And so the limit of this is also 5, because x or n or t, well, x simply disappears. So this limit is actually 5. This is not the shortest way of dealing with a limit like that. Not the shortest, not the most efficient. So it's actually not the best thing. I have seen people trying to transform exponential limits to this kind of logarithmic limit, but that actually means more complicated work. It's not really making things easier. So I would say doing things separately is just fine. Taking separately what is inside the logarithm, dealing with what is inside the logarithm, with this part, and then going back, putting the result into the logarithmic expression. All right, so now we have methods like standard classical methods for 0 over 0, canceling out the 0 factor, or if we have radicals, we also multiply it by the conjugate and then cancel out the common factor. We had infinity over infinity. We have had, in many cases, infinity minus infinity, which needed to be transformed. We had 0 over 0 trigonometric limit, and we had 1 to power infinity, this e-limit thing. So we have had several methods. We have seen that using the conjugate sum is actually one very, very good approach in many cases. Now we will see another approach, another possible approach to many limits, not all of them, but many. So comparison of infinitesimals. Infinitesimals, please remember, an infinitesimal was a function that is infinitely small, that becomes infinitely small in the process when the x value tends to something. It might tend to whatever value, or to infinity, or to 0. So remember that infinitesimals are usually denoted by alpha and beta or other Greek letters, but not by the Latin letters, the normal letters. So suppose we have two infinitesimals. An infinitesimal means that the limit of this function is 0 when x tends to that point, and the same happens with b. So how can we compare? If they are both infinitely small, are infinitely small things all similar? Or do they group somehow? Are some infinitely small quantities more similar than other infinitely small quantities? And the answer is yes, it is. It is possible to compare infinitesimals. And let's suppose we can consider the limit of the ratio of the two infinitesimals. So we have two expressions, both of them tend to 0, but we have a ratio of those. And let's suppose that for some reason it is possible to evaluate this limit. So suppose we have the limit of the quotient of two infinitely small functions about the point x0. Then what could happen to x? What could happen to x? Well, several things. X could be a constant, not x, but sorry, c. C could be a constant. In other words, we have two infinitesimals, but the ratio tends to be constant when x becomes very, very, very large. And then we say they are of the same order. Of the same order in the sense of they are comparable as in commensurable. You can measure them together and you see that they are basically the same, about close to the point x0, of course. Then we might have one of them of a higher order than the other one. So the numerator has higher order, an infinitesimal of higher order than the denominator if the limit is 0. And it's the other way around. It's the other way around. We can say beta is of higher order than alpha if this ratio tends to infinity. Because in that case, I think it's the other way around, sorry. Alpha is of high, no, everything is correct. It is correct, it is. We also, oftentimes we denote, if we say alpha is of higher order, it means alpha is a stronger, infinitely small thing. It's infinitely many times more infinitely small than the other one. So we denote it as alpha is O of B, small o, small letter O. It's alpha is O of B. We generally use it to write down the idea that alpha is of higher order than beta. And what else? What we have remaining, one special case only remains. That is, if c is 1, then we say these two functions are equivalent. If c is 1 for infinitesimals only, we cannot do this with limits, with functions that are not infinitesimal, with functions that do not, by themselves, they do not tend to 0. So equivalent. We already know some equivalent infinitely small functions. For example, if alpha is sine of x and beta is just x, then we could say, okay, these two are equivalent when x tends to 0. When x tends to 0, of course, not everywhere, but if x tends to a special point. We already see equivalent functions. We know equivalent functions are also tangent and x, and arctangent and x, and the arcsine of x. So all these functions we consider in the trigonometric limit, they are equivalent, because when you find the ratio, this ratio tends to be 1, basically. And how do we use this? Oh, we use this sign. So in principle, I could say sine of x is equivalent to x if x tends to 0. Sine of x is equivalent to x when x tends to 0. For example, like this. There are other equivalences. In fact, we will use those. We will consider those. And this will actually explain the method. This will explain the method. Another nice and easy method. If you know how to use it, it's actually very simple. And so we will start by comparing the two infinitesimals. So alpha is the infinitesimal, simply y equals x. When x tends to 0, of course, x tends to 0. That's fine. So to compare them, we always need to consider alpha divided by beta. When x tends to, in our case, 0. We simply write out the comparison, but the comparison happens in a fraction form. So this will be limit when x tends to 0 of alpha is x and beta is sine square of x. We in fact see that we have limit x tends to 0, x divided by sine x times sine x, there's nothing else. So yes, this part tends to 1, not 0, but 1. And in principle, we see that we have the limit of 1 divided by sine x. When x tends to 0, the sine value, what happens? The sine value also tends to 0. All in all, if we just look at this limit, it actually is 1 divided by 0. 1 divided by 0. 1 divided by 0 is infinity. So this means now going back, this means that beta is of higher order than alpha. The bottom function is a stronger, infinitely small quantity than the top function. So this, for our case, this means that sine square of x is higher order than x. Or I can write beta of x is O small of alpha of x. This is O. Higher order, that is stronger, infinitely small, much smaller than alpha. So sine square x is much smaller than x when x approaches 0. So we found the limit as it can be seen, and I will now just erase this. So we find the limit. So alpha is x and beta is 1. Beta x is sine square x. As we already saw, this limit is actually infinity because we had 1 divided by 0. This limit is infinity, which means, as I already said, beta is of higher order, O small of alpha of x. Beta has higher order than alpha, stronger infinity. Similarly, we can compare these infinitesimals just by writing down these limits. I'm not going to write these limits, but so what we would do to check this, is alpha over beta, so it will be x divided by arc sine x. In fact, we know that this limit is 1. So we could say that, in fact, in this case, alpha of x is equivalent to beta of x because the limit is equal to 1. X divided by arc sine divided by x, the same value 1. So if the ratio tends to 1, then these functions are called equivalent. Similarly, we would need for this case, for this next case, say x tends to 0, alpha to beta. That is limit x to 1 minus cosine 2x. I am not writing this, I am not doing this, but in principle, this limit would be infinity. Again, the function 1 minus cosine 2x is stronger, infinitely small. It's infinitely smaller than just x. That is interesting. 1 minus cosine 2x is smaller, infinitely smaller than just x. So this kind of comparison, there are all kinds of possibilities for limits. I really don't want to do these limits at the moment. They are there from the older times. So equivalence of infinitesimals. The equivalence of infinitesimals is the most important part from this particular part. So the good thing is that if we have equivalent infinitesimals, in certain situations, not every time, not everywhere, but in certain situations, we can substitute one for the other. That is, if I have a limit of a ratio of two infinitesimals, so if I have a limit of a ratio, one infinitely small expression, one function that is infinitely small and the other function that is infinitely small, in this case I'm writing them as f and g, then if these are both infinitesimals, I can replace them by the functions to which they are equivalent. I can replace them by the functions where they are equivalent. So, for example, if this is alpha, then instead of alpha, I can actually write beta, the other function to which it is equivalent. Why do we need to choose this? That is, if we know some equivalent functions that make the situation simpler, that simplifies it, then we can find the limit quite easily. Let's see, what equivalences do we already know? We, first of all, when x tends to 0, we already know these. Because the ratios, all the ratios of sine x to x, tangent x to x, arc sine to x, arc tangent to x, all these limits actually are equal to 1. That means that sine x is equivalent to x, tangent x is equivalent to x, and so on. Also, they are equivalent among themselves, of course, in this situation. But we can, in fact, when we have a more complicated limit, we might want to substitute an expression like this by just x, for instance. And if, of course, I have something else, if I have 5x, then I substitute it by 5x. And then there are others. So, for example, when x tends to 0, there's another equivalence. This expression is also equivalent to x. E to power x minus 1 when x tends to 0. E to 0 power is 1. So this expression actually does tend to 0. It turns out it can be proved, by the way, using our last limit, this 1 to power infinity, the E limit. Using that limit, it can be proved, in fact, this equivalence, but we will not do that. We will simply use it. So e to power x minus 1 is equivalent to x, which means in a limit, we might be able to substitute it for something. Natural logarithm ln of 1 plus x is also equivalent to x when x tends to 0. When x tends to 0, there are some possibly very nice examples with this. So this actually means that I know that in a situation where I have limit of ln of 1 plus, let's say, 5x divided by e to power 2x minus 1, this is a crazy limit when x tends to 0. Looks rather crazy, but what happens here is, because this is infinitesimal, because ln of 1 is 0, e to power 0 is 1, so the denominator is also equal to 0. But in this ratio, in a limit of a ratio, I can substitute these for their infinitesimals. That is, ln of 1 plus t, or ln of 1 plus x, is equivalent to x. So if I have 1 plus 5x inside the logarithm, I can substitute it is equivalent to 5x. ln of 1 plus 5x evidently then will be equivalent to 5x. Now, in the denominator, if e to power x minus 1 is equivalent to x, I could say, all right, that means that e to power 2x minus 1 is equivalent to 2x. Keeping these equal, so I can substitute that by 2x. And now this limit, or not infinity, this was 0. This limit is actually 5/2. So these equivalent infinitesimals are in fact incredibly useful, because otherwise some of you would say, okay, let's use L'Hopital's rule, what not, differentiate. Why? If we can use infinitesimals, the solution becomes extremely simple. So I seriously hope that at least some of you will consider this method before you try something more complicated. So what else? 1 minus cosine x. This is that final method I said. So we could use trigonometric expressions, we could use the multiplication by conjugate sum, but we can also directly apply equivalence. We can apply the equivalence directly. So whatever we have in the cosine, if it tends to 0, we can substitute this expression by the equivalent expression x squared over 2. Getting rid of cosine, getting rid of trigonometry altogether immediately. An example for that would be one of our, let's say, familiar limits. We had 1 minus, I don't know, cosine of, let's say, 4x divided by x sine 3x, for example, when x tends to 0. How to deal with a trigonometric limit using this method? Remember that normally we said, okay, let's multiply by the conjugate, let's get sine square of 4x, and then we divide it by 2 and everything. So in principle, I would say 1 minus cosine 4x can be substituted by 4x squared divided by 2. Because instead of x, of course, in the cosine we have 4x, then that means in this formula, instead of x, we need 4x. Don't forget the parentheses, otherwise you will get the numbers wrong. So we can substitute this by 4, okay, limit. Let's do it as a limit, in the limit form. This will be, using this substitution here, cosine of 4x is equivalent to this. So I'm writing 4x squared divided by 2. X is, okay, x is x. And sine of 3x is equivalent to 3x. And so as a result, we see x squared and x squared will disappear. We have 4 squared divided by 2 divided by 2 times 3. This is 16 divided by 3, or 8/3. So this can be solved using the trigonometric limit by transformation, or it could be solved by simply substituting the equivalent infinitesimals. So there are just a few, there are not so many. So The first four are already familiar with our trigonometric limits. And then there's one more. And then there's one more. I will now clean up the board a little bit, not everything perhaps, but I will clean up this part, the explanation. I will clean up this part because I will want to write something. I will want to write something. So I will actually also clean up this so it looks nicer. And now we have another interesting equivalence where alpha is any real exponent. Alpha is any real exponent, which would mean that, for example, 1 plus x cubed minus 1 is equivalent to 3x. And that's it. Or square root of 1 plus x minus 1. Square root means power 1/2. Alpha is 1/2 in this case. So this is equivalent to 1/2 of x. So these things can be useful in the more complicated limits. These things can be useful. And for the, okay, we have, our time is up. In fact, we have to finish. In the end, let's see in the next lecture, which is next Wednesday, please, we will have a look at some, you see, these crazy looking limits, unpleasant looking limits that can be solved perfectly easily using these equivalences. So for comparison of infinitesimals, this previous part, this previous slide, where we had to compare the infinitesimals, this part, this is less important. From this, the important part is this equivalence. If the ratio of two functions is 1, and if these functions are both 0, so if 0 to 0 is in some situation equal to 1, then these functions are called equivalent, and that means we can actually use these equivalences. And next time we will have more examples of this. Next time we will also on Wednesday discuss continuous functions in connection with limits. And then next week, Friday, we have the 4th unit test. A reminder, I did put it in Ortos, but people tend to ignore or not read things. So Monday, the 3rd of May is free. It's because and May 4 is also free because it's a national holiday. So Monday from the 3rd of May is moved to Saturday the 8th. We will have Monday schedule on that day, like Monday. This will be like Monday. So our next time is on Wednesday. We will meet on Wednesday, both for elementary mathematics, where we will have test 3, and for mathematics 1, where we'll finish up limits. Then we meet on Friday when we rate the 4th unit test, and then we meet on Saturday where we have, let's say, the next lecture, simply the next lecture. So that's next week. We will.
Yes, but for Friday, we using Friday schedule?
For Friday, yes. For Friday, yes. It's only that we take Monday from the 3rd of May and move it as it is to Saturday. That's it.
Okay, thank you.
It's just as it is. We simply take Monday as it is, and we move it to Saturday. That's how they replace or move the working days. All right, so that's it for now. I would like to remind you that if you start missing the class unit test during lecture time too much, then unfortunately I have a lot of work to do these days, because it seems that all groups are having all kinds of examinations, and I have tons of papers to mark, tons of work to do. So I can't actually perform consultations and test retakes every week. It's simply impossible. I don't have that much time. I don't have that kind of time. So please make sure you attend class tests when they are supposed to take place. All right. So I guess some people are coming back at past to retake the third unit test. Some people are coming back at 5:30 to retake the vectors unit test. And for the rest, I will say goodbye until next Wednesday. So 4 free days. Enjoy your 4 free days.
Thank you, Miss. Same to you.
Thank you, Professor.